figure here is what we have for the surface heat flux. For point number 0.1, the surface temperature, the heat flux only goes up to here. So we are losing a considerably large amount of data here if we only run the experiment for 0.1, point number 0.1.
Okay. So where the what you say that the slope, yes, the slope of the graph intersect with the surface temperature, it indicates the adiabatic wall temperature, and the slope representing the heat transfer coefficient. And next, the experimental method. A flat plate heat transfer experiment was conducted. As you can see here, the data for the surface temperature, which is in black line, and the air temperature is being represented by the dotted line. The surface temperature doesn't look very good compared to the previous one, because this is a artificially plotted graph, and this is how the real experimental graph will look like. This is the most stable condition I can get from the experiment. So with a velocity of 27 meters per second, the experimental time was conducted quite long, which is half an hour, which is represented by Fourier number 0.95. The data analysis for the surface temperature will involve two solutions. One is the two temperature solution, and the other one will be the Crank-Nicolson heat conduction. The reference will be from flat plate heat transfer coefficient. So the result for the two temperature solution, which is based on Pony et al. 2012, which uses the Fourier one-dimensional semi-infinite heat transfer solution. For Fourier number 0.1, which is the time limitation for the semi-infinite solution, the theoretical heat transfer coefficient will be 89.2. The air temperature at the end of the experiment is 36.9. And over here we have the result for the heat transfer coefficient from the two temperature solution, which is 95.5, around about 10% overshoots the theoretical heat transfer correlation. And the adiabatic temperature is 36.2, which is quite close to the air temperature during the experiment. So if we use more surface temperature for the data analyzed, for Fourier number 0.95, the heat transfer coefficient will be much lower than the theoretical heat transfer coefficient, but the adiabatic wall temperature is the same. If we use the Crank-Nicolson heat conduction solution, in which the boundary conditions are the same with the semi-infinite solution, for Fourier number 0.1, the results is quite similar to the semi-infinite solution, and also the adiabatic wall temperature is the same, almost the same as the air temperature. But if we extend it to Fourier number 0.95, the result will be off for the heat transfer coefficient. Only for the heat transfer coefficient, the adiabatic wall temperature will be the same. So this is how the results for the heat flux looks like. For Fourier number 0.1, as you can see, there are no data at the lower portion of the graph. For Fourier number 0.95, we have an extra data over here. Even though with the considerably more, almost half of data, additional data, the results is not, I would say, it's not correct. This reason being that the boundary condition used for the Crank-Nicolson solution is not meant for foil number 0.95. But for foil number 0.1, the results is quite similar to the typical one-dimensional semi-infinite heat transfer solution, 95.5, 95.6. So the conclusion is the time limitation for the one-dimensional semi-infinite transfer was pointed out, which is the foil number 0.1 is quite short for heat transfer experiment. And if we can use more surface temperature data above foil number 0.1, we can have much more data for the data analysis. So the Crank-Nicholson solution was chosen as an alternative solution. The results show good agreement with theoretical value for foil number 0.1, but for foil number above 0.1, the Crank-Nicholson could be applied, but with modified boundary conditions. This will be on my future work. So that's all. Thank you very much. I hope there are no questions. This is very simple. No, please.
So we've heard the request from the speaker. If you do have any questions, you can still ask.
Yes,
just a quick one.
I'm honored.
Right. You showed the comparison just now.
Yep.
I can see that. Is it that both the data, chemical as well as the
Semi-infinite solution.
within the error for theoretical as well as for the experimental? What are the errors?
Yeah, the errors. I haven't plotted out the errors. It will be on my future work. But this is actually a part 2 of the paper. In part 1, there's I plotted a correlation between the theoretical heat transfer value and also the Crank-Nicholson heat conduction solution. For a wide range, for this experiment, I only use one free stream velocity, which is 27 meters per second. In the previous paper, there will be a range of velocities which end up with a range of theoretical heat transfer values. So if you plotted that, the errors, if I'm not mistaken, are less than 20%, which is acceptable for heat transfer experiments.
Okay, another one, what is the range of the Reynolds number? You mentioned 27 meters per second this time.
I'm sorry, I cannot remember the. Oh, you have a pointer. I don't have. I can't remember the Reynolds number for this.
In the laminar region or in the turbulence region or in the transition?
Well, because we are using a transient mesh heater at the inlet of the experimental tunnel, so the flow will be turbulent from the get-go. For this, if I'm not mistaken, the range of the Reynolds number will be around 10 to the power 5, if I'm not mistaken. That will be in the transition section if there are no turbulence inducer in the experimental rig. So if there are no mesh heater in front to induce the hot air, then we have to go beyond 10 to the power 5, maybe 10 to the power 6 to be in the region of the turbulent heat transfer section. Turbulent heat transfer region, yes. Thank you. Wait.
Any more questions with regard to heat transfer? No? Okay, let's just assume that you can ask after the session during lunch.
Thank you very much.
Yes, thank you, Danny. We're invited to take a photo together outside. All the speakers and participants, they set up like a photo place the booth. So so let's do that now. And then